So, continuing on our discussions with respect to designing lead compensators in the frequency domain, making use of the Bode plots. So, let's just recall what we had in the last lecture. So, specifications, the performance specifications were usually in terms of the gain and the phase margins. This were like what determine the transient performance together with the error constants in terms of the position, the velocity, or the the acceleration error constant. So what happens in the frequency domain? So we saw that the lower frequency region decides my steady state performance in terms of a certain Kp, Kv, or a Ka. Region 2, where the gain margin and phase margin kind of concepts come, they determine the relative stability and the transient performance, and the higher frequency region determines how we are handling noise, is it amplified or not, and so on. So, here we would be interested typically in region 1 and region 2, and we will see how we go about looking at a design problem. Okay, so we just look at the sinusoidal transfer function, and then we plot the response of Gc times G. So, if Gc can be written as K prime Gc prime with the gain coming out explicitly, then Gc times Gc j omega times G j omega can be written down explicitly like this, right, and then this guy can actually go into what we also can say as the plant dynamics. Okay, so what we did in the roost locus, when we had a problem where we wanted to compensate for the transient performance and also ensure a certain steady state error or certain bounds of the steady state error, we first designed the transient controller, which is essentially the lead compensator, and then went on to design the steady state compensation, which was a lag compensator. So here we do a slightly different approach, right? The first step would be to meet the steady state specifications, and it will be obvious in the next few slides of why we need to meet the steady state requirements first, right. So, in order to meet the steady state requirements, so we look at the frequency response of this thing, right, and then we choose the gain K prime such that the steady state specifications are met, and once the steady state specifications are met, we choose an appropriate controller, which we denote here as Gc prime, to achieve the desired gain margins and the phase margins. So, this is how my transient performance specifications are stated to me. They are given to me in terms of the phase margin and the gain margin, and we know that there actually exists a one-to-one relation between the phase margin and the and things like the damping coefficient and all. Okay, so the first step in any control design is to just start with a proportional controller, as we did even in the root locus. So we mapped the given transient performance specifications to a set of dominant poles, and if the dominant poles were lying on the open loop root locus, we just compute the gain at that location and say, well, I can just design a proportional controller of that particular gain to ensure my behavior in terms of the transient performance. So, similar thing we will also do here, right. We begin first with a proportional controller. So, well, just to make things a little easier, let us start with the help of an example, that I am given a G of S, the plant as 4 over S, S plus 1 with specifications of this form, that the overshoot should be less than 15% and the settling time of less than 5 seconds, which translate to appropriate zeta and omega n. Well, we know the formulas for this, and which in turn translate to a phase margin of 53 degrees, right, and a certain gain crossover frequency of 1.19. Okay, and in addition, I am given that the steady state specifications which I should meet is 40 per second. Okay. Now, just look at the open loop Bode plot, right. So, here the open loop things would tell me that my phase margin is 28 degrees, and I know how to find out the velocity error constant from the Bode plot. I just extend this line and find the frequency at which it intersects the 0 dB line, and that frequency is actually my Kv, right. So, this was what we did when we were discussing how to find out error constants just by looking at the Bode plot. So, the specifications or the open loop system has the following characteristic, that the kV is 4 and the gain margin is 28, and we would like to have it something like this, that kV should be 40 with a phase margin of 53 degrees. Okay, so let us just start with a proportional controller where Gc is just k. So, what changes in the magnitude and the phase? Well, the log magnitude changes according to this thing, 20 log k times g of j omega. So, you see that this gain k just adds up this magnitude to my open loop frequency response or open loop Bode plot, right. This is my plant. Okay. The phase angle remains the same. So, with a proportional controller, the Bode magnitude plot shifts by this number 20 log k, the phase plot remains the same. Okay. But this is, well, the phase plot remains the same, but something strange happens here. Let us say I start with this plant and I say I just keep on increasing my gain to see what happens. Okay. So, I keep on increasing the gain and I see that what happens is with the increase in gain, this Bode plot shifts, the magnitude plot shifts up. Okay. And when it shifts up, what we see is that this frequency, which we call as the gain crossover frequency, this keeps on shifting to the right. So, even though the phase plot remains the same, the phase margin changes because the phase margin is defined now at the new gain crossover frequency. So, if I just keep plotting some of this and I see that my phase margin actually keeps on decreasing as I arbitrarily keep on increasing the gain, and that is essentially because this changes, this frequency changes, right. So, I am just corresponding to these things, I just keep going here. Okay. Even though I see that an improvement in my steady state is visible, right. So, because this frequency at which the initial slope intersects the 0 dB line will tell me what is my kV. So, I really want it to be as further as possible. Okay. So, for a gain of 10 k, gain of k equal to 10, I have kV equal to 40, but the phase margin is highly unacceptable. It is just 9.04 when the original system had a phase margin of 28 and the desired is 53. Okay. Now, what we observe is that, well, when I just do a proportional controller, well, I have a big trade off between the steady state and the transient specification, right. So, based on this plot here, what I see is that to achieve a desired steady state performance, or if kV should be large, this actually means that the gain in region 1 should be as high as possible to achieve low steady state errors, right. So, if you see here, right, this keeps on increasing, and if this keeps on increasing, my kV goes on increasing, and therefore, my steady state error decreases. Okay. Now, the region 1 thing is taken care of. Now, I want to do something over here in such a way that my phase margin requirement is also met. Okay. And this is where we come to this point of designing a lead compensator using Bode plots. Okay. So, the transfer function of the lead compensator is exactly the same as we did in the time domain, where I have a gain, a 0, a pole where pole was significantly to the left of the 0. I could write it in time constants in this way, and this is my sinusoidal transfer function. And as usual, alpha would be less than 1, right. So, I am looking at designing Gc j omega as k prime Gc prime, but this guy is the Gc prime, and k prime just takes care of the gain factor here, that is alpha times k, right. So, first we design this k prime, the gain which ensures a desired steady state performance, and then I go about finding what are these numbers here. The unknowns are the omega, unknown is the capital T, and unknown is the alpha. Okay. So, just by making alpha less than 1, well, I know that the pole is to the left of the 0 on my complex plane. So, a typical Bode diagram, the asymptotic plot is given in the black, it would look something like this. Okay. And then you see that the phase actually has a nice shape here. So, if I go back and compare to what was happening earlier, you see that the low frequency region, right. So, here, so this is my region of interest, right. So, nothing much should happen over here. So, what I see is that the low frequency region, the addition to the gain is very small or almost 0, similarly with the phase. So, I am not really interfering with the low frequency region. However, here I see that, well, the phase margin should increase, which means this plot should be pushed to the right. So, sorry, to further a little up to ensure a bigger phase margin, and this curve here ensures that I push the phase margin or push the phase plot to slightly upwards, so that I have the desired phase margin. Okay. So, now the lead compensator is now essentially seen as a high pass filter, right. You can see that for higher frequencies you have a higher gain and so on. Okay. So, and unlike the proportional controller, the lead compensator raises the Bode magnitude plot at only high frequencies, not at the low frequencies, right. So, nothing is happening at the low frequencies. So, I am ensuring something in the mid frequency range without actually disturbing my low frequency range. Okay. Now, if you see how this plot goes, there is a point where the phase attains a maximum value and then it again goes back close to 0. Okay. Now, there is a frequency at which this compensator provides the maximum phase lead, right, and this frequency is what we will use in the design process. Okay. Now, what is this maximum phase lag and what are we trying to identify here? We are trying to identify these two corner frequencies and this alpha, right. So, once we know these two corner frequencies, we know the alpha, then our design process is complete. Okay. Now, the angle which the compensator provides is given by this one, right. So, I have a tan inverse of omega t coming from the numerator and then negative of tan inverse of alpha omega t, right. And then you see that this angle phi, which is angle contribution here, it varies with frequency and it has a maximum at a particular frequency. This is like a nice looking continuous function. So, I can just find the maxima of it, right. I can say what if I ask myself a question, what is the frequency at which phi c attains the maximum value, and calculus tells me that just do this thing, d phi by d omega is 0, which leads to me to these expressions, and I say the omega at which the maximum phase occurs is just this one, omega is 1 over square root of alpha times t. Now, this frequency is the geometric mean of the two cutoff frequencies. So, I see this is one cutoff frequency at 1 over t and this is a cutoff frequency of 1 over alpha t, then this is just the geometric mean of both of them, right. So, the frequency at which the maximum peak occurs is a geometric mean of these two cutoff frequencies. Okay. And then we conclude that the maximum phase lead occurs at this particular frequency. Okay. Now, at this frequency, how does phi of c look like? Well, in this expression, now I know what is this omega, right, where maximum phi of c occurs, that is this one. So, I substitute this expression into the computation of the angle and I do all these things and I see that the maximum phase lead is related to alpha via this expression, just a simple computation, right. Then first I find out what is the frequency at which the maximum phase lead occurs, I substitute it into this expression and I get what is the maximum value of phi c. So, two questions, what frequency? Well, it occurs at this frequency, the maximum phase lead. What is the value at maximum phase lead? Well, that value of that angle is written down in terms of alpha with this, just little steps here. So, given alpha, I can find a phi m or vice versa. So, if given how much phase lead I need to add to the system or how much should be the extra angle contribution, I can find out what is alpha, right. So, in this expression now I find out alpha, right. So, phi m is sin inverse of 1 minus alpha over 1 plus alpha, and this occurs at this frequency. Okay, now what is happening to the magnitude at this frequency, right? So somewhere here, and this magnitude is at omega equal to omega m is 20 log 1 over square root of alpha. This also can be computed pretty easily, right? I don't really need to derive expressions, so we already know via Bode plots of how we do this, right? So I am just substituting in this expression these values which I compute, right? So substitute omega equal to 1 over square root alpha t in this expression, find out what the magnitude is, and I just get this one. Okay, 20 log 1 over square root alpha is the magnitude at this frequency. And what is this frequency? This is the frequency at which the maximum phase lead occurs due to the compensator. Okay, now let us come back to the design problem. So I have g of s is 4 over s plus 1, and then I translate all these again to specifications to in such a way that I want gamma or the phase margin to be 53 degrees together with kV of 40 per second. So the open loop characteristic is that gamma is 28 and kV is 4, as we have seen even earlier. Okay. So first is, well, can I at least first take care of my steady state requirements? Well, how is the steady state requirement? So kV, the velocity error constant, is s times the entire transfer function. So the entire transfer function consists of this k prime, gc prime, g of s. So what I know is that if I look at this expression, limit s tends to 0 for my gc prime is always 1. Okay, why is that obvious? That is obvious because just substitute omega equal to 0 here, you always get 1, right? So this really does not contribute anything to that thing. And that is also an indication that nothing really is happening with this compensator for the steady state error. It does not really contribute anything, either positive or negative. So I am just left with these expressions. Kv is k prime, limit s tends to 0, s times g of s. What is required? Kv is 40, right? And I know that limit s tends to 0, s times g of s is 4. This is given to me, right, from here. Limit s tends to 0, s times g of s is just 4, and then so I can just find out the new gain k prime is just 10, 40 over 4, or this is the additional gain that my compensator should provide, right. With k prime equal to 10, I can get kV is 40. Okay, now I just simply add this compensator and I just plot k times g, right. So this is my controller, the proportional controller, which gives me a steady state error constant of 40. And okay, what happens to the Bode plot? Well, this is fine, right. This initial slope intersects at 40 radians per second, and this is the value of my kV. Okay, I look at this gain crossover frequency and I find something terrible has happened here, is that the phase margin has reduced to 9 degrees, right, with this gain k. So I want this guy here, the phase margin, to be like 50 degrees. Okay, so I put if I just say, well, I want to put a controller here such a way that okay, so if I do something like this, then the phase will increase to give me a desired phase margin. This is essentially what I want to do. I want to add some angle here, right, add an angle such that the new gamma is 53 degrees. Okay. Now how will we do this? So here the gain crossover frequency is roughly about 6.28, right, you can just see from this plot here. Okay, so I have to perform this operation in such a way that the effect here is minimum, right. So that is what we even said that. So now given that the steady state performance is satisfactory, I must choose a compensator that does not disturb this low frequency content, right. And then if I look at a lead compensator, as I said earlier, that it is a high pass filter and provides no attenuation to low frequency signals, no gain, no attenuation also. Right. Okay, now we also require that the additional phase margin at the gain crossover frequency to meet the transient specifications, right, and then this lead compensator provides me that additional thing over here. So this actually should not be 9, but this should be somewhere like close to 50. Okay. Now this is what we will achieve with the help of a lead compensator. Okay, now let us just do some experiments, right, to say, well, now I want to design a compensator which looks like this. The only information I have is alpha is less than 1 and I know the k prime which gives me a kV of 40. Okay. So, we want to select alpha and t in such a way that I should meet the desired specification. So, I just play around with different values of alpha, right. So, for different values of alpha, the Bode plot of the compensator looks something like this, right. So, there is an angle here and then the frequency at which the maximum angle occurs keeps on shifting to the right and you have the magnitude plot going this way. Okay, and you see the low frequency behavior more or less remains the same, right. There is nothing happening in this region. So, we are not really playing around or we are not really disturbing what is happening to the kV. Okay. So, now we require an additional phase angle at the gain crossover frequency, right. So, this is how the phase margin is defined, right. The amount of phase or 180 minus the formula. Now, where do we compute this? We compute this at the gain crossover frequency. Now, at this gain crossover frequency, the angle should be 53. Okay. Now, I already have an angle of 9.04. Now, how much should the lead compensator give me? Well, I have through this computation that the lead compensator should give me an additional angle of 44 degrees at this point. If this is this angle plus 44, then I am fine, right. I am my transient specifications are met, my steady state specifications are met and I am happy. Okay. So, how do we go about this? So, here well this is my gain crossover frequency 6.28 and I add this much of angle at this frequency. That is what I would naturally do, right. So, that this is my gain crossover frequency and what I need is angle, the overall angle here to be like 53 degrees. Okay. Now, let us just do this, right, arbitrarily. Okay. Now, what I know, how do I compute these things? Well, I know that phi m is related to alpha via this formula, right. So, phi m is the additional amount of phase my controller or the compensator needs to provide. So, for this phi m, it turns out that the alpha is 0.179. Now, this phi m, the maximum phase lead, I know that it should occur at the gain crossover frequency, right. Here I want this to be 53 over here at this frequency. Now, this frequency will be my omega m. Okay. Now, once I know omega m, I know alpha, I can find out what is the t, right, because this omega m occurs at the geometric mean of these two cutoff frequencies. So, now I know alpha, I know what is the omega m, so I can compute what is t, okay, based on the formulas which we derived. Now, I know k prime, I know omega, I know. So, I don't really need to know omega, right. I know the omega m. Based on this omega m, I compute what is alpha and what is t, and this is how my compensator would look like. Okay. Now, let us verify if this is actually helping me get the desired phase margin or not. Now, the Bode plot, I would now see the plot of not just g of s, but it will be k prime, right. With this k prime gives me a kV of 40 per second. Now, I have g and I also have gc. This is my gc. G is given to me as a plant. Now, I just draw these things and I find out, well, what is the phase margin. The phase margin actually turns out, so I should look at the phase margin not of g, but now of gc times g of s. Okay, gc times g of s, this is this is where I will measure the phase margin, right? This is the gain crossover frequency of the compensated system. I go down and I check, well, it is not 53, but it is actually 43. Okay, what has gone wrong here? So, if I just compare the Bode plot of the uncompensated system, what I see is that there is a change in the magnitude plot in such a way that my crossover frequency is no longer at 6.28, but it is somewhere here. And we designed our compensator such that the maximum phase lead occurs at this frequency. But that does not really satisfy the closed loop conditions, because this point has shifted to the right, and therefore we should have gamma at this new crossover frequency to be 53, not here. This is not useful to me. Okay. So, just by looking at this crossover frequency and designing a compensator does not help me much, because the gain crossover frequency of the compensated system shifts to the right. That is obvious, because you see there is a little bit of a magnitude change also, right, in the characteristics of the compensator. Not only the phase changes, but also the magnitude changes. Therefore, the natural tendency is that the gain crossover frequency will shift to the right, because you are actually adding up some magnitude, right. Okay. Now, how to fix this problem, right? Because of the positive magnitude contribution of the lead compensator, the gain crossover frequency naturally shifts to the right, and the maximum phase contribution from the lead compensator, it no longer occurs at the new gain crossover frequency, it occurs still at the old gain crossover frequency, but we want the 53 degrees to be at the new gain crossover frequency, right. So, at the new gain crossover frequency it is 43, but I really want 53. Okay. Now, well, how do we know, right? So, now I know already that the Bode plot shifts to the right. So, can I appropriately find a new gain crossover frequency? Well, one technique is okay. So, instead of 43, this should have been 53. So, can I actually convert this 53 which I was designing to be here to be some 63, for example. So, if this I push it a little further up, this will naturally go up, right. So, that is one technique. The new gain crossover frequency, the phase contribution should be greater than by 10, right. So, what I should then do is I should shift this by some extra 10 degrees, which means that even though this is going down here, this can be 53, and the phi m here can be much higher, right. So, I just add up 10 degrees here, so that I compensate here. Okay. Now, if I design for phi m equal to 54, I can find the appropriate alpha again from the same formula, nothing changes here. Okay. Instead of 44, now just to compensate for this shift, I am adding some 10 here. Okay. So, with this new alpha, I can find, well, now we must fix the t, right. Now, how do we fix the t? This is the question. Now, look at what happens at omega m. At this omega m, if I go back to what my Bode plot does, we just take a much simpler one, the first one here. Okay. At this omega m, there is a certain shift in magnitude here, right. So, this is the extra magnitude contribution, right, to my closed loop Bode plot, and therefore, it shifts a little to the right, and therefore, I select omega m. At omega m, I do not know this omega m, but I know what is the contribution of the magnitude. So, based on what we had derived earlier, this one, I do not really need to know omega m, but I know that at a particular omega m where the maximum phase lead occurs, the contribution of the magnitude plot is 20 log 1 over alpha. Okay. Now, in this example, that turns out to be 20 log 1 over alpha, with this new alpha turns out to be 9.79 dB. Okay. Now, what do I do? If we choose omega m to be the frequency at which the magnitude of the gain compensated system is the negative of this, then omega will be the new gain crossover frequency. Okay, let us again go back to our plot and see what this means. Now, this is the old gain crossover frequency. This does not help me, right. Now, what should be the condition at new gain crossover frequency, call it omega c. Okay. At this the new frequency should be such that G, I can put a K prime, G of j omega Gc of j omega, the 20 log of this should be 0, okay, which means that now I know what is this at the new crossover frequency, right. I can just compute it by 20 log 1 over square root of alpha. So, it should be such that, so if this is my 20 log square root of alpha, say whatever, this is 9.7 here, then at this this is the new frequency which I will choose, because at this frequency, right, here the magnitude of G by itself is negative of 9.7, this entire guy K times G, and what I am adding to this negative of 9.7, I am adding now a positive of 9.7 which comes from the compensator, so that the overall contribution becomes 0, okay. Now let us see this statement again. Choose the omega m to be the frequency at which the magnitude of the gain compensated system, that is K prime times G, is minus 9.7, right. Then omega m will be the new crossover frequency, okay. Now from the Bode plot I can find out what this is, right. This frequency is found out to be 11.2 radians per second. Now once I know the omega m, I could compute easily what is the t. Once I know the t, I can get the structure for the compensator, and what this gives me is, well, this is kind of very nice here. So this gives me a gain margin of 59, well, which is perfect. This is exactly what I want, right. And well, the gain crossover frequency here is 11.2, right. So this is how we just do it a little bit by trial and error to find out, to compensate for the shift in the Bode plot to the right, right. So there was, when we added a lead compensator to the root locus, it was pulling it to the right. Here the magnitude plot shifts slightly to the right, and therefore I need to find out what is the new gain crossover frequency. This new gain crossover frequency is just a frequency at which the gain compensated system has this much of magnitude contribution, okay. So this is how it's done, right. So this is with the help of a very simple example. Other examples would also follow the same nature of it, right. So there is nothing really complicated about taking a system which has 4 poles and 3 zeros and things like that, okay. So this was a very simple and yet powerful illustration of how we design lead compensators in the frequency domain. So the idea was just, okay, so then the thing was, first I need to find out what are the locations of the poles and zeros. First, unlike the root locus, I here first compensate for the steady state behavior and then come to the transient behavior. So I again, as usual, compute what is the phase lead, I compute the new gain crossover frequency, and I have now techniques of how to compute the new gain crossover frequency, and based on that I can find out what is my alpha and t, which will give me the location of the poles and the zeros. So similarly, next time we will see how to design lag compensators and eventually leading to lead and lag compensators using Bode plots. Thank you.